So in this video, we'll talk about what's known as Lenz's law. It's very closely related to Faraday's law, but there's one important distinction, right, that differentiates the two that I didn't really tell you about in last video. Okay, so let's see. We have two examples here of a bar magnet. In both cases, they have the orientation the same. North is on right, south is on left. And it's in close proximity to some non-conducting, or rather, it's a current loop, it's a conducting loop, but there's no current initially running through it, okay? There is a current that does run through it because the flux is changing. So on the left side, the flux is actually increasing because, well, this permanent bar magnet is moving towards the loop. So remember what magnetic flux is. One black. Phi b is the closed integral of b dot dA. That's the magnetic flux. So on the case at left, out of the north into the south, those field lines in green are passing through that area of pi r squared, whatever it is, that closed area. And because the magnet is moving closer and closer, the flux is increasing. Specifically, the strength of the magnetic field is increasing. So we can write it like such. There is an EMF in this case because it's increasing. And so the EMF induces a current that's actually running, let's see, this side is in the foreground, this is in the background. So that I that they've shown there is really an induced current, which means that it's created based upon another mechanism, right? And so that's created because the magnetic field strength is increasing through that area. In other words, the flux is increasing, okay? Now, you may notice, if you've done the right-hand rule, that it's actually backwards to what your right hand should show you. If you put your fingers in the direction inside the loop that the green arrows show you, well, that would mean your thumb is pointing down over there and up over there. That's backwards to what's shown. That's because that current is the induced current. I know I keep saying that, but that's important, right? It's reversed to the normal direction of the right-hand rule because of Lenz's law. And Lenz's law is simply the fact that, I should have left a little space, is simply the fact that you can put a minus sign in front. That's all Lenz's law is. So, tell you what, let me write that a little bit larger. So the EMF is now, with Lenz's law, d phi dt is negative d dt closed integral b dot dA. Lenz's law is that minus sign right there. That's it. The rest of this expression is Faraday's law. So this is a minor but very important distinction and part of Faraday's law. And so this current induced is negative to what the right-hand rule should tell you. And there's a reason for that. The electromotive force, or EMF, that arises because of this change in flux, the induced current wants to reduce that EMF back to where it was. Okay? So on the case on the right, since the flux is increasing, the induced current arises and tries to decrease that flux back to where it was. Right? So if you use the right-hand rule now with the induced current, there should be a magnetic field pointing, let's try and do it here, back that direction, inside the loop. So we can call that the induced magnetic field from the induced current. And so this acts to, well, try and decrease the magnetic field from the permanent magnet. Right? It won't necessarily cancel it completely out, but it works to try and decrease it. That's why it's in the opposite direction, and that's why there's this negative sign right there. Okay. On the right-hand side, the flux is decreasing. Right? The value of the magnetic field inside that cross-sectional area right there is getting smaller and smaller and smaller because the magnet's moving further and further away. And so, because of that change in flux, there's an induced current, again, I, right there, such that it orients itself to then resist that change. So that induced current, well, wants to increase the flux now. And it can only increase the flux if it creates a magnetic field pointing in the same direction as the permanent bar magnet. Right? So using your right hand, putting your thumb, at least on this foreground piece, downwards, that means your fingers should curl inside the loop and point to the right. That's the same direction. It basically wants to try and add back magnetic field onto the permanent bar magnets, right? Thus increasing the flux back to where it was, at least trying to. Right? So this, again, is the negative. It's always opposite to what you might think with the right-hand rule from the magnet, okay? And so in the previous video, I did not include this minus sign because I was going to explain it here. Right? So this is actually the full entirety of Faraday's law, which incorporates Lenz's law. Okay. And so this electromotive force is, well, negative, the change in flux over time. Thanks for watching.